Welcome to the video lecture on sum and difference formulas. We are going to derive in this lecture identities involving the trigonometric functions of the sum and difference of numbers or angles. Recall that cosine alpha plus beta does not equal cosine of alpha plus cosine of beta. In other words, you're not allowed to distribute this cosine across parentheses. That's a common mistake by students. Let's see why it's not true. And all you have to do to show that it's not true is find a counterexample. Find an alpha and a beta that show that this is not true. So I am going to just pick alpha to be pi and beta to be pi over 2. Just two common nice angles. So let's figure out what cosine of pi plus pi over 2 is. And we're trying to show and prove that it's not equal to cosine of pi plus cosine of pi over 2. So what's pi plus pi over 2? Well, this is like 2 pi over 2 plus 1 pi over 2, so this is 3 pi over 2. And cosine of 3 pi over 2, that's the same as 270 degrees on that y-axis, on the negative y-axis. So the cosine value would be the x value there, which is 0. So cosine of 3 pi over 2 is 0. Now on this side, cosine of pi, that's on the x-axis, the negative x-axis. So cosine of pi is negative 1, and cosine of pi over 2, that's on the positive y-axis, so cosine of pi over 2, or 90 degrees, is 0. So negative 1 plus 0 is negative 1, and obviously 0 does not equal to negative 1. So we've just shown that for these two angles, pi and pi over 2, this is not true. You're not allowed to distribute that cosine across parentheses. So it's true in general that you can't do that for any trig function. So if you have any trig function of an a plus or a minus a b, you're not allowed to distribute that trig function across and just do the trig function of a plus or minus the trig function of b. So if cosine of alpha plus beta does not equal cosine of alpha plus cosine of beta, then what does it equal? Well, we're going to derive the proof for what it equals next. So here's what we're going to need to do. We have to prove or figure out what cosine of alpha plus beta is. So what we're going to do is we're going to draw a picture here. There's a unit circle, and I'm going to let this dot over here be p sub 0. It's going to have coordinates 1, 0. And then I'm going to let q sub 1 be right here, where this arc length right here is beta. So that means its terminal point would be cosine beta, comma sine beta. Remember, your terminal point is your x and your y value, and the x is the cosine and the y is the sine. So q1 has coordinates cosine beta, comma sine beta. Then I'm going to go from where q1 left off, and I'm going to measure out an arc length of alpha right here, and where that stops is going to be p sub 1. So the net arc length that I'm going through from here all the way to here is alpha plus beta. So its terminal point would be cosine alpha plus beta, comma sine alpha plus beta. Okay, that's the x and y coordinates of this dot. It's just the terminal point of this whole arc length going across. Finally, we're going to let q sub 0 be over here, and it's going to be, this arc length will be minus alpha. So the same distance as alpha, but going in the negative direction from point p sub 0. So its terminal point, its x and y value, will be cosine of minus alpha, sine of minus alpha. So whatever this angle is here, the x is the cosine of that angle, and the y is the sine of that angle. Okay, so I've created these 4 points, and the first thing I want you to notice is that since cosine is an even function, cosine of minus alpha is really the same as cosine of positive alpha because it's even. And since sine is odd, sine of minus alpha, we're allowed to pull that negative out front because it's an odd function. So q sub 0 is really the same as cosine alpha, comma negative sine alpha. So just simplifying that a little bit. Now the next thing I want you to notice is the distance between point P sub 0 and P sub 1, so from here all the way to here, that distance is the same as the distance between Q sub 0 and Q sub 1, from here to here. And the reason why they're the same distance is because they're covering the same arc length. This is the net arc length alpha plus beta, and from Q0 up to Q1, that's also an alpha plus a beta. So if those two distances are the same, then the chord, which is the little line segment connecting P0 to P1, and the chord between Q0 and Q1, those two chords must have equal lengths. So the distance between those 2 points, using our distance formula, has to equal the same thing on both sides. Okay? So what we're going to do, now that we know coordinates of P0 and P1 and coordinates of Q0 and Q1, is we're just going to use the distance formula to figure out what these two distances are, and we're going to force them to be equal to each other because that's how we constructed our picture. So remember how to find the distance between 2 points. It's this great big square root, and you subtract the 2x coordinates squared, plus you subtract the 2y coordinates squared. It's kind of like that Pythagorean theorem. So for the points P0 to P1, we're going to subtract these two x's from each other. It doesn't matter which one you start with. So I'm just going to start with the cosine alpha plus beta. That's the first x. And I'm going to subtract the second x value, which was 1. And that quantity squared gets added to the difference in the two y coordinates. So this y, sine of alpha plus beta, minus 0. So that's the distance between point P0 and P1. Now let's do the distance between Q0 and Q1. So we're going to subtract these two x's. So this x and this x. So cosine beta minus cosine alpha, quantity squared, plus the difference in the two y's. So this y minus this x. So sine of beta minus negative sine of alpha, quantity squared. You do get a double negative there, so it's going to turn positive. Now the rest of this is just algebra. So now what we're going to need to do is try to clean all this up. And the first thing I'm going to do is get rid of the square roots. If they're both under square roots on the left and the right side, the only way two square roots can equal each other is if the stuff under the two square roots is equal to each other. So in other words, we're squaring both sides to get rid of that square root. So let's ignore that. It doesn't have an impact on the answer. And then the rest of what I'm going to do is basically just foiling out all of these quantity squareds. Okay, so let's start with this quantity squared right here. Remember, you have to FOIL. So I would take this term right here and square it. And then I would multiply it times a minus 1, and I'd get 2 of those. So minus 2 cosine alpha plus betas. And then I'd get a minus 1 times a minus 1, which is a plus 1. So all 3 of these terms is what I get from foiling out these two x's being subtracted. Then we go to the y's. Now this was 0, so really we just have a sine squared alpha plus beta, because there wasn't anything subtracted off, so we don't have to FOIL, we're just squaring the sine. So that's my left side. Now on the right side we need to FOIL out this expression, so I'm going to get a cosine squared beta. I'm going to get a middle term, a minus 2. I'm going to have a cosine alpha and a cosine beta in that middle term. And then I'm going to get a positive cosine squared alpha. So I get all 3 of those when I FOIL out this quantity squared. And then finally over here, when I FOIL this out, I'm going to get a sine squared beta. I'm going to get a positive 2 sine alpha sine beta. And I'm going to get a positive sine squared alpha. Okay, the next thing I want you to notice is one of our identities. Normally we write it as cosine squared x plus sine squared x equals to 1. But you can generalize this. This is cosine of stuff plus sine squared of that same stuff always has to equal 1. As long as these two angles match each other, then the cosine squared plus the sine squared of that matching angle has to equal 1. And that's important because that's what we have right here. We've got cosine squared of stuff plus sine squared of that exact same stuff. So these two things become a 1. So on this left-hand side, we get 1 plus this one as well, which is a total of 2, minus this middle term, minus 2 cosine alpha plus beta. Now let's look on the right side. On the right side, what we notice is that we have a cosine squared beta plus a sine squared beta. So there's a 1 right there. And then we also have a cosine squared alpha plus a sine squared alpha, which is also a 1. So we're going to get a 1 plus a 1, which is a 2. And then we have left over are the two middle terms. We get a minus 2 cosine alpha cosine beta from this middle term, and then we get a positive 2 sine alpha sine beta. Now if we go to solve this equation, because that's what we were trying to do, we were setting these two distances equal to each other so we could try to solve. What I would probably do next here is subtract that 2 to the other side, and notice it cancels out on both sides. So now we have negative 2 cosine alpha plus beta, and notice that both of these terms have 2's and they have negatives involved. So what I'm going to do is factor out a negative 2 from each of these terms. So that will leave me with a cosine alpha cosine beta, and this would have to be a minus sine alpha sine beta, so that if I were to redistribute that negative 2 across, I'd get back this plus 2. Now the reason I'm factoring out that negative 2 is because then I can divide both sides by that negative 2, and now we have a formula. Cosine of alpha plus beta equals cosine of alpha cosine of beta minus sine alpha sine beta. So it's not a simple distributive property. We can't just distribute this cosine across the parentheses. What we end up getting is the cosine of the alpha times the cosine of the beta as well, minus the sine of alpha sine of beta. So the sine that's right here is opposite the sine that's over here. So on the next page, you'll see, we'll write down the conclusion here. So for cosine alpha plus beta, what we just came up with was that this was cosine of alpha cosine of beta minus sine of alpha sine of beta. In a similar way, with a similar proof, you can show that cosine of alpha minus beta is cosine alpha cosine beta, so same way that this is set up, but instead of a minus here, this is going to be plus sine alpha sine beta. So the thing to remember with cosines is that you have alternate signs. Whatever sign is on the left side, you need the opposite sign on the right side. Now with a similar proof using cofunctions, you can also prove for sine of alpha and sine of beta what these are. So this is going to turn out to be sine of alpha cosine of beta. Notice it's different. It's not sine sine, it's sine cosine. This is a plus in between, and then this is cosine alpha sine of beta. So it's a little bit different than our cosine sum and difference formula. For cosine sum and difference, it's cosine, cosine, sine, sine. For sine, it's going to be alternating. So sine, cosine, cosine, sine, and the other thing that's different is the signs are the same. So if it's plus on the left, it's also plus on the right. And for the sine alpha minus beta, this is going to look the same, sine alpha cosine beta, and since this is minus, this is going to stay minus cosine alpha sine of beta. Now the proof of these sine ones, there's an easier way to prove it than going back to that whole diagram that we did to prove the cosine sum and difference formulas. What you can use is the fact that we have cofunctions, and we know that sine of x has to equal cosine of its complement. So cosine of pi over 2 minus x. This is this idea of cofunctions. that sines and cosines have equal values for complement angles. So we can use this idea here to solve this problem or prove this identity. What we could show is that if we wanted sine of alpha plus beta, we can turn that into its cofunction, which would be cosine of pi over 2 minus alpha plus beta. And then if we just distribute the negative here a little bit and make this pi over 2 minus alpha minus beta, what I'm going to do is I'm going to group these first two together. And then I'm going to apply this sum formula that we just learned up here, or actually the difference formula that we just learned up here, where I'm going to think of all of this as my new alpha and this as my beta. So according to my difference formula, we're supposed to take cosine of this whole first angle times cosine of the second angle. And then we use the alternate sign in between, so since this was a minus originally, I want a plus here. And then we take sine of this whole first angle times sine of the second angle. And then using that cofunction idea again, cosine of pi over 2 minus alpha is the same as sine of alpha, because pi over 2 minus alpha is the complement of alpha. So this becomes sine alpha cosine beta, and I'm just using this formula again, this cofunction identity right here. And instead of using x's, I'm just using alphas. So that's where this turns into that. Similarly, sine of pi over 2 minus alpha becomes the cosine of alpha. Those are cofunctions again. So this is our proof. We've just proven that sine of alpha plus beta is sine times cosine plus cosine times sine. Okay? All right, the last sum and difference formulas that we're going to learn are for tangent. You don't need to know the ones for secants, cosecants, and cotangents. You just need to have them memorized for sine, cosine, and tangent. And we're going to prove what this formula is by just trying to solve this or rewrite this expression, tangent of alpha plus beta, in a different way. So let's see if we can prove this. So first thing I might do is change tangent to sine over cosine. So tangent of this whole sum becomes sine of this whole sum over cosine of this whole sum. And then what we can do is now use these new sum formulas that we've learned for sine and cosine. We've already proved what they are, so let's use them. So sine of a sum is sine of the first angle times cosine of the second angle plus cosine of the first angle sine of the second angle. Then for cosine sum, it's cosine of the first times cosine of the second minus sine of the first sine of the second. Now the next thing that I'm going to do is a little bit tricky. It's probably not something that you would normally think of doing, but what I'm going to do is I'm going to factor out a certain expression. I'm going to factor out cosine alpha cosine beta from the numerator and from the denominator. So if I were to factor out cosine alpha cosine beta from this top expression, what would have to be left over so that if I were to redistribute across, I would get back this original numerator? Well, what I would need to have on top here would be a sine of alpha over a cosine of alpha. And let's see why. If you were to redistribute, the cosine of alphas would cancel out, and you'd be left with sine of alpha cosine of beta, which is exactly this first term right here. So that works. Now, let's see what would be left from here. I'm pulling out the cosine alpha, so that's already out. So what would be left is this sine of beta, and then I would need a cosine of beta in the denominator, so that if I were to redistribute this across, the cosine betas would cancel out, and I'd be left with cosine alpha sine beta. So I'm just kind of doing some fancy factoring. Let's do that again for the denominator. If I factor out a cosine alpha, cosine beta from this first term, that pulls everything out and just leaves me with a factor of 1. If I pull out a cosine alpha, cosine beta from this second term, it doesn't have either one of those. So what I would have to have left is that sine alpha would still be there, that sine beta would still be there, and I would need a cosine alpha, cosine beta on the bottom so that if I were to re-multiply, those would cancel each other out, giving me back just the sine alpha, sine beta that I want to have in the bottom. Okay, so I did a little bit of fancy factoring there. Now the nice thing to notice about this factoring is what I pulled out of the top is exactly what I pulled out of the bottom. So that makes me have like factors on top and bottom that I can cancel out. The other thing to notice is that sine alpha over cosine alpha is tangent alpha. And sine beta over cosine beta is tangent beta. And in the denominator, we get that 1, and then we get that minus. Sine alpha over cosine alpha is another tangent alpha, and sine beta over cosine beta is tangent beta. So what we have just proven is that tangent alpha plus beta is tangent of alpha plus tangent of beta. So that's kind of like if you were just distributing the tangent right across, but there's a denominator. On the bottom you have 1 minus tangent alpha, tangent beta. What happens if I change this sum into a minus? Well, it's exactly the same proof, but the only thing that's going to change in terms of our final outcome are the signs are going to switch. So tangent alpha minus beta is tangent of the alpha minus tangent of the beta. So the signs on top should be the same. And then on the bottom you get 1 plus tangent alpha, tangent beta. So the signs on the bottom should be different. So to summarize, here's a list of all of these sum and difference formulas where you have a sum of two angles or a difference of two angles. And these 6 you do need to have memorized. So for cosines, sines, and tangents. Okay, so I would expect you to have these memorized. You will not be allowed to use a note card or a formula sheet on these particular formulas. So let's see how we can use them to help solve some problems. First thing we want to do is find the exact value for sine of pi over 12. So in order to find the sine of pi over 12 and find its exact value, the only way we know how to find exact values for trig functions is if it comes from one of our nice angles, like our pi over 3s, pi over 4s, pi over 6s, pi over 2s, things like that. And pi over 12 is not on that list. So what we want to do to be a little bit creative here is think of a way of getting pi over 12 using some of our known good angles. And what you want to notice is that pi over 12 is 4 pi over 12 minus 3 pi over 12. And 4 pi over 12 reduces to pi over 3, and 3 pi over 12 reduces to pi over 4. So instead of finding sine of pi over 12, I'm going to change this into pi over 3 minus pi over 4. This is now a difference of two angles, so I'm going to use this difference formula for sine, since we're taking the sine of it. So according to this difference formula, you take the sine of the first angle times the cosine of the second angle, use the same sign in the problem. So if this is a difference, this is going to stay a difference, and then you switch it up. So now we're going to do cosine of the first angle and sine of the second angle. And now we want to simplify that, and we can because we know the terminal points for pi over 3 and pi over 4 angles. For pi over 3, remember that has as its ordered pair 1/2 for the x, root 3 over 2 for the y, and pi over 4 is root 2 over 2 for both x and y. Sine is your y value, x is your cosine value. So sine of pi over 3 is this root 3 over 2. Cosine of pi over 4 is root 2 over 2, right here. Cosine of pi over 3 is this 1/2. And sine of pi over 4 is that root 2 over 2. So I was able to get all of those exact values by being a little tricky and changing pi over 12, which was not one of our good angles, into some of our good angles. And then to simplify here, root 3 times root 2, those are both square roots, so I can multiply underneath, and this becomes root 6 over 4. And then 1 times root 2 stays root 2, 2 times 2 becomes 4. And if you want, you could consolidate this into a single denominator of 4 and make it root 6 minus root 2. And that would be your exact value. When it asks for the exact value, you should not be giving decimals, because decimals are just approximations. So you should leave the radicals in your answer. Okay, let's try this again. This time I want to find the exact value for cosine of 105 degrees. So again, we want to be a little bit clever here. 105 degrees is not one of our good angles. We want to use pi over 3s, pi over 4s, pi over 6s. And remember, those are like 30s, 60s, and 45s. So is there a way to use 30s, 60s, or 45s to get to 105 degrees? Yes. 105 is 45 plus 60. And 45 is like pi over 4, and 60 is like pi over 3. So cosine of 105 degrees is really cosine of 45 degrees plus 60 degrees. So we're taking a single angle and we're turning it into a sum of two angles. Now, in order to evaluate this, you have to use your sum formula for cosines. It's not just going to be cosine of 45 plus cosine of 60. According to our sum formula for cosine, it's cosine of the first angle times cosine of the second angle minus, you use opposite signs, sine of the first angle, sine of the second angle. Now remember, 45 degrees is the same as pi over 4. So cosine of pi over 4 is root 2 over 2, and so is sine of 45 degrees. 60 degrees is the same as pi over 3. So cosine of pi over 3 is 1/2, and sine of 60 degrees is root 3 over 2. So it's kind of the same exact expression almost as the last one, but this time we just get the different order. So it's root 2 over 4 minus root 6 over 4, or root 2 minus root 6 all over 4. Okay, one more example here. Find the exact value for secant of 7 pi over 12. So again, 7 pi over 12 is not one of our known angles, so if we want an exact value, we're going to need to turn it into pieces of angles that we do have exact values for, namely pi over 3s, pi over 4s, pi over 6s, pi over 2s. Well, hopefully from some of the other problems we've already done here, you can see a fairly easy way to get 7 pi over 12. We can make it 4 pi over 12 plus 3 pi over 12, and each of those reduces. We get pi over 3 plus pi over 4. So, in order to get secant, we need to know how to find a cosine, because we don't have up here in our list any sum and difference formulas for secant, but we do have sum and difference formulas for cosine. So we're going to have to work a little bit outside of the scope of the problem for a moment. We can't find secant directly. Instead, what we're going to do is first we're going to find cosine of 7 pi over 12, and we're going to do that by changing 7 pi over 12 to the sum pi over 3 plus pi over 4. Once we know what the cosine value is, we can find secant by just taking the reciprocal. So how do we find the cosine of this sum? It's cosine of the first times cosine of the second minus sine of the first, sine of the second. Pi over 3 is like 60 degrees. Cosine of pi over 3 is 1/2. Cosine of pi over 4 is root 2 over 2. Sine of pi over 3 is root 3 over 2. Sine of pi over 4 is root 2 over 2. So we get root 2 minus root 6 all over 4. just like we had for some of the earlier ones. Now remember, this is what cosine of 7 pi over 12 is. So secant of 7 pi over 12 needs to be the reciprocal of this. So we have to flip it over. So 4 over root 2 minus root 6. Now it depends on your instructor. Usually I'm fine with leaving radicals in the denominator, but if you're checking answers in the back of the book, or if you have a different instructor, they may require you to rationalize the denominator, which would require you using a conjugate. So I'm going to have to multiply by root 2 plus root 6. So this becomes 4 root 2. Remember that there are parentheses here, so you want to distribute. Plus 4 root 6 all over. Root 2 times root 2 is 2. You're going to get a minus root 12 and a plus root 12, so those will cancel out. And then you'll get a minus root 6 times a plus root 6, which is minus 6. And 2 minus 6 is a negative 4. So all these 4s are going to cancel. You can pull that negative out front if you want and make it negative root 2 plus root 6, or you could distribute the negative across. Either way is fine. Okay, next example. Find the exact value for cosine 40, cosine 10, plus sine 40, sine 10. Now, the way that this question is structured, it should look very, very similar to our sum and difference formulas. And it had cosine, cosine, sine, sine, and there was a plus in the middle. So if we look at our formulas up here, cosine, cosine with a plus in the middle, and then sine, sine, that's a difference. Cosine of the difference of whatever the alpha is minus the beta. So that means that this is the same as cosine of whatever this angle alpha is minus, because we want opposite signs, whatever this beta is. And 40 minus 10 is just 30, and this is degrees. And 30 degrees is the same as pi over 6. And cosine of pi over 6, that x value is root 3 over 2. So that's our exact value. Okay, next couple of examples. Remember those cofunction identities that we use to help prove our sine and our sine, sum, and difference formulas? Well, we're going to prove them here. We proved them in other sections before, but we're going to go ahead and prove them again using our proving of trig identities process. So let's say that we wanted to prove cosine of pi over 2 minus u is equal to sine of u. So according to our difference formula for cosine that we now know, we can take the left side of this equation and we can apply our difference rule to it. So it would be cosine of the first angle, cosine of the second, plus sine of the first, sine of the second. Now pi over 2 is 90 degrees, and the x value at 90 degrees is 0. The y value at 90 degrees is 1, so sine of pi over 2 will be 1. So this all goes to 0, and 1 times sine of u is just sine of u. So that's why that cofunction idea is true. Cosine of an angle is equal to sine of its complement. Let's try it for sine. Same idea, but this time we're going to apply the difference formula for sine. So it's sine of the first angle, cosine of the second, minus, use the same sign, minus cosine of the first angle, sine of the second. Remember, sine of 90 degrees is 1. Cosine of 90 degrees is 0. So this all goes to 0. 1 times cosine of u is cosine of u. So we got it. Okay, let's try our next proof. We want to prove this identity. Cosine of x plus y plus cosine of x minus y is just 2 cosine x cosine y. So let's go ahead and start. I'm going to go ahead and start with that left side because it looks in the form of our sum and difference identities that we just talked about. So if we start with our left side, cosine of x plus y plus cosine of x minus y, Here we have a sum. So for cosine, it's cosine of the first, cosine of the second, minus sine of the first, sine of the second. And then for this difference, it's cosine of the first, cosine of the second, plus sine of the first, sine of the second. And those sine x's and sine y's cancel out, and these two are like terms because they're the same, so if we add two of them together, we're going to get 2 cosine x's, cosine y's. And that's what we wanted, so we got it. Okay, let's try to prove the identity. Cosine of 3 pi over 2 plus theta is equal to sine of theta. So it's kind of similar to that cofunction idea. We're going to start with that left side because we've got a sum going on there. So we're going to do cosine of the first, cosine of the second. We want a minus because for cosine it's opposite signs. Sine of the first, sine of the second. Now 3 pi over 2, remember on your unit circle, that's down here. So it has coordinates 0 for x, -1 for y. Cosine is the 0, the x value. So this goes to 0. So we get just a big 0 for that whole first term. And the y value is the sine, so this goes to -1. So this is all gone, and a minus minus becomes plus sine of theta. And that's what we wanted, so we proved it. Okay, the next example here, this is something that you will see again in calculus. It's very important in the idea of derivatives, and it's part of the proof that the derivative of sine of x is cosine of x. So we're not going to go all the way throughout to show that because you need to have some ideas in calculus to be able to finish this proof off. But we are going to do the algebraic part of the proof. Now to show this, we're using something called a difference quotient, and you've seen these before. It's f of x plus h minus f of x all over h. And we want to apply this difference quotient formula to the function sine of x. So let's see how to do that. So if our function is sine of x, and we want to find our function evaluated at x plus h, remember that what that means is to take this whole expression x plus h and use that as the new input into your function. So instead of taking sine of just x, we want to take sine of this whole quantity x plus h. So that's what f of x plus h is. Then we want to subtract from that f of x. This time we want our input to just be plain old x. So I want sine of just plain old x. And then we're taking all of that and we're dividing it by h. Okay, so that's what our difference function, our difference quotient starts out looking like. We can simplify it a little bit because this piece right here is a sum for sine, a sum of two angles. So we can use that sum formula, and this becomes sine of the first angle, cosine of the second, plus cosine of the first, sine of the second. And I still have that minus sine x on the side as well. Then what I'm going to do is I'm going to regroup these a little bit. I'm going to just flip-flop these two terms around so that I can get this sine x term next to this sine x term. So this would become sine of x cosine h. And then I'm going to put the minus sine of x in the middle, and I'm going to put the cosine x sine h on the end. And then what I'm going to do is, since these two have sine of x's, I'm going to factor it out, and in parentheses I would be left with cosine of that h minus 1. I'm not factoring anything out of this last term on the end. And then last but not least, I'm just going to break up this great big fraction into two separate fractions. So this fraction and this fraction. So we'd get sine of that x, and then I'd have that cosine h minus 1, and I'm going to put that all over h. Notice I'm purposely doing my fraction bar like this instead of doing it all the way across, even though that's implied, just to make it look more like what I'm trying to turn it into. And then similarly for this last piece over here, we'd have that cosine x and that sine of h, and all of that is over h, but that would be the same as just the sine h over h, because this is implied to be over a 1. So you don't have to do the entire fraction bar if you don't want to. And I'm just trying to make it look more like the original problem. So we get that sine of x, and then we have this cosine h minus 1 over h, and then we have cosine x times that sine of h over h. And what you will go on to learn in calculus is that as h gets really, really small and goes closer and closer to 0, it turns out that this goes to 0 as well, and this goes to 1. So what you're left with is just cosine of x, and that's called the derivative. So what we prove in calculus is the derivative of sine of x turns into cosine of x. And you don't need to know that for this class, but that's an application of what we're doing here. Okay? So let's take a look at this next example. It's going to lead us into our last topic for this lecture. Take a look at 1/2 sine x plus root 3 over 2 cosine x. And we want to try to rewrite this in terms of a single sine function. Right now it's a sum of a sine plus a cosine, and we want to rewrite it in terms of just a single sine, sine of some angle. So how could we do that? Well, it has the look sort of a sum or difference product, or sum or difference expression that we've been talking about. If we go back up to our formulas way up at the beginning, if you look at these for sines, it's a sine times a cosine, and then either plus or minus a cosine times a sine. So let's compare that to what we have to work with down here. So imagine this 1/2 times this sine plus this root 3 over 2 times this cosine. So you have kind of a cosine or a sine value here and a cosine or a sine value here. And those numbers should look very familiar to you because we see them quite often when we're talking about some of those nice angles on our unit circle. These are the numbers that are associated with pi over 3s and pi over 6s. And in fact, 1/2 is the same as cosine of pi over 3, and root 3 over 2 is the same as sine of pi over 3. So if we were to rewrite this way instead, what you would see is you've got cosine of an angle times sine of an angle plus sine of that angle times cosine of an angle. In other words, this is like a sum of two sines, and it's a sum because there's a plus in between. And what are the two angles that I'm adding? I'm adding the x, and I'm adding the pi over 3. Now you could put the pi over 3 first. It really doesn't matter which angle comes first because it's commutative property of addition. But what we've done is we've rewritten this sum of sines and cosines into a single sine of an angle. And sometimes that's important to be able to do, again, for applications in calculus and so forth. So what we're going to show down here is basically a formula for how that's always possible to do. If you have any expression of the form a sine x plus b cosine x, and that was kind of like what we had up here, a sine x plus b cosine x. The a and the b were these coefficients in front. A and b can be any real number. If you have anything of that form, you can always turn it into some constant k times sine of x plus, and this is called phi. This is the Greek letter phi. K turns out to be the square root of a squared plus b squared. And to figure out what phi is, cosine of phi is a over this big square root, and sine of phi is equal to b over this big square root. So I'll show you how to do this in just a minute, but first let's go ahead and prove that this is really true. So what I'm going to do is I'm going to start with this right-hand side over here, and I'm going to work with that because it has a little bit more stuff that I can work with. The first thing I'm going to do is I'm going to take this sum and apply my sum formula to it. So it's going to be this k times sine of the first angle x times cosine of the second angle phi plus cosine of the first angle x, sine of the second angle phi. Now what is k? They tell me what k is. K is this great big square root. And they tell me what cosine phi is. It's all of this expression here. So I'm going to leave sine of x the way it is, and I'm going to substitute in for cosine of phi a over square root of a squared plus b squared. And then over here, I'm going to leave cosine of x the way it is, and I'm going to change sine of phi into all of this expression. So b over square root of a squared plus b squared. Now what happens when I distribute this square root across? It's going to cancel out both of those square roots in the bottom. So what we're left with is an a and a sine of x plus a b and a cosine of x, which is exactly this left-hand side that we were trying to prove. So there's the proof. Now let's see an example. So on this last problem, what I have here is the graph of 3 sine x minus 6 cosine x, and I'm just showing you a glimpse of what it would look like from a graphing calculator. So does it kind of look like a single sine function? I mean, the actual formula for it involves sines and cosines. It's a subtraction of a sine minus a cosine. But if you were just looking at the graph and you had no idea what its formula was, does this look like a sine curve? Yes, because it has that nice sine shape that we're used to. And you can actually pick out part of that sine curve shape right here. So there's a typical sine curve shape. Okay? Now if you were to look at that particular cycle right there, what would you say that its period is, approximately? Well, from here to here is 2 pi, and notice this hits a little bit after that first dash, and this hits a little bit after that first dash after 2 pi. So this whole length here looks to me like it's got a period of 2 pi. What's the amplitude of this graph? How high does this go? Well, it looks to me like it's maybe around 7 or so, somewhere in there approximately. And then finally, what's its phase shift? So how far over does this start? And that first little dash right there, let's put these in so you can see them a little bit more. Where are these dashes at? Here's pi, and I've got 3 equal sized dashes. So this is pi over 4, pi over 2, and then 3 pi over 4. So it's a little bit between pi over 4 and pi over 2. So let's just estimate it to be around, what's between pi over 4 and pi over 2? Pi over 3. So it's approximately shifted over to the right by pi over 3. And if you're actually shifting right, remember that that would be showing up as a minus inside the parentheses, right? So you would have sine of x minus pi over 3 in your equation. So what we're going to do now is, these are our guesses for what this equation might look like. We would kind of guess that it's going to be a sine curve with an amplitude of 7 and a phase shift to the right by pi over 3 with a normal period of 2 pi. And what we're going to do next here is we are going to rewrite this function that we had that graph of in terms of the sine only, using that formula that we mentioned before. So the formula was that a sine x plus b cosine x could be turned into k sine of x plus phi. Now let's find this k first. The k was defined to be the square root of a squared plus b squared. And the a is this 3, and the b is this negative 6. So this is going to be the square root of that 3 squared plus that negative 6 squared, which is 9, plus 36, which is 45, which is, if you reduce it, if I pull out a 9, that's 3 root 5. So k is approximately 3 root 5. Now what we want to do is find out what our angle phi is. I know what this k is. Now I need to know what phi should equal. So to figure that out, we were told that cosine of phi was defined to be a over this square root of a squared plus b squared, and sine of phi was defined to be b over the square root of this a squared plus b squared. So let's figure out what that is. Well, a again was 3, and square root of a squared plus b squared was 3 root 5. We already figured that out down here for our k. So to figure out what phi should be, we would need to do an inverse cosine. And if you do that on your calculator, kind of depends on which mode you're in. This is either 63 degrees, or if you're in radians, about 1.107 radians. Now the only thing I want to show you with this sine of phi is it's going to give you the same value, except we have to worry about our signs here. Because b is negative 6, and this square root of a squared plus b squared is that 3 root 5. So which quadrant are we supposed to be in if the cosine is positive and the sine is negative? Which quadrant has cosine, or x, being positive, but sine being negative? That's quadrant 4. So both of these answers that I gave down here for phi were angles in quadrant 1. So that's not quite the right phi that I want to use. I want to use something based on these answers that I gave here, but I want it to be equivalent to this angle in quadrant 4. So an easy way to turn a quadrant 1 angle into an equivalent quadrant 4 angle is just to make it negative. So instead of going up 63 degrees, we just go down 63 degrees. So in other words, the phi that we're going to use would either be negative 63 degrees or negative 1.107 radians. So what does all this mean? What did we just figure out? So what it means is that this function right here, let me go down here a little bit just to kind of summarize what we've just come up with. So the original function, which was 3 sine x minus 6 cosine x, according to this formula, what we just figured out was that this was equal to k, which was 3 root 5, times sine of x plus phi, and our phi was minus 1.107 radians, or you could do minus 63 degrees, whichever units you want to. So what we're saying is that this function here is really equivalent to this function here. Now, if this was your formula, just looking at that formula, what would you say its period is? Well, since there's no number being multiplied by x, there's no horizontal compression or stretch. So the period isn't going to be changed at all. So the period of this new formula over here is 2 pi. What's the amplitude? It's 3 root 5. And what's the phase shift? Because of the minus, this would be to the right. And it's a shift to the right by this number right here, which is about negative 1.107 radians. How does that compare to what we guessed up here? Well, we got the same period. 3 root 5 is close to root 7, and 1.107 is close to pi over 3. So we were able to guess from the picture what the right amplitude, period, and phase shift was, but this formula enabled us to figure out exactly what that period, amplitude, and phase shift would be. So that's kind of the benefit of this formula. Okay? All right, some more formulas and identities that you do need to have memorized. Sum and difference formulas for cosines, sines, and tangents. Please memorize those for all tests and homework and so forth. All right, good luck. That concludes our lecture on sum and difference formulas.